Hello all, myself Suma R, working as Assistant Professor in Department of ECE, MIT, Mysore. So today we will be discussing about the Boolean algebra and logic circuits. So under this, let us take the first topic, binary numbers. So first let us understand what is a number system, then we will move on to the binary numbers. What is a number system? A number system is one which is used to represent the information in quantitative format, right? So now if you consider number system, that too in computer language we have 4 number systems. In this we have decimal number system, then we have binary number system, next we have octal number system, then at last we have hexadecimal number system. So these are the 4 number system we usually use in digital logic or in digital language. Yes, now if you consider the binary number system, so let us understand how to represent the number in binary number system by considering decimal number system first, because decimal number system is the one which is we are very familiar with. Therefore, so let us consider number in decimal. Later we will arrive at general representation for any number system for that matter. Yes, let us consider a number, say for example 8954. So we read it as, or we write in compact format. So if you write the expanded form of this number, so how do we write? So we write this in expanded form as 8954. So this is how so the expanded form of this compact number is represented. But usually we never represent any number in expanded form, we usually go for compact form. So this is the compact form in decimal number system. Therefore, so if you observe, so here this can be written in another format as 8 into 10 to the power 3 plus 9 into 10 to the power 2 plus 5 into 10 power 1 plus 4 into 10 power 0. Yes. So if you observe carefully, so we have some coefficients here. So we are not using the powers of 10 to represent the number in the compact form. Instead, we are using only the coefficients to write or represent any number. Therefore, so in general, we can represent the number in terms of coefficients. Let me start from A5. Here we have only 4 digits. So I am starting, since we are writing in general, so I am taking some higher coefficients also. A5, A4, A3, A2, A1, A0. So if you consider this number, whatever I have written here, so here we have A0 as 4, A1 as 5, A2 as 9, A3 as 8. So I have considered 2 extra digits here. So if the number is in fraction format, then we write like this. So A minus 1 dot after the decimal point. So we write A minus 1, A minus 2, A minus 3, etc. This is how we can represent any given number using its compact, that is coefficient. Using the coefficients, we represent the number in compact format. So this is the representation of a given number in decimal number system. Now, so coming to the binary, so as I said, let us generalize. Let us generalize and let us represent general equation for any number system. So how to represent a number in any number system. So later we will consider the binary. Now let us generalize and let us represent the equation for any number system. The generalized equation for representing any numbers in any number system. Let us consider the base radix as r. Okay, if that is the case, using these coefficients we can represent the general equation like this. So a5 into r to the power 5 plus a4 into r to the power 4 plus a3 into r power 3 plus a2 into r power 2 plus a1 into r power 1 plus a0 into r power 0 plus, so we need to represent, okay, the numbers after the decimal point. So they are represented like this: a minus 1 into r power minus 1 plus a minus 2 into r power minus 2, a minus 3 into r power minus 3, etc. Now, okay, so this is the general format for representing any number, okay, in terms of its coefficient. So for example, if I consider this number, so I have already written the representation of this. Now let me consider, okay, the digits after decimal point also, okay, the fraction numbers. Now, so how it is represented? Let me change here itself, okay, here the expanded form. So I have represented 8 into 10 power 3 plus 9 into 10 power 2 plus 5 into 10 power 1 plus 4 into 10 power 0. How it will be continued? Plus, okay, you can observe that, plus. So we need to write the next coefficient a minus 1 into 10 power minus 1. So r power minus 1 we have written. So here, since the base is 10 for the decimal number system, radix or base is 10. Therefore, so we need to, okay, multiply the coefficients by, okay, the weighted powers of the radix. So here we have 7 into 10 power minus 1. Next will be a minus 2. A minus 2 is 5. Okay. Then, so will be multiplied by 10 power minus 2. So this is how we represent, okay, or we write the expanded form using the general equation. Fine? Yes. Now we need to discuss binary numbers, because the topic what we have taken is binary numbers. So now let us move on to the binary number system. So binary number system is a special number system, because we have only two values there. So one is 0, the other one is 1. Only two values are there. Therefore, using those two itself we need to express all the numbers whatever we use, we need to represent using only 0 and 1. So now the coefficients what we have here, a0, a1, etc., all this will be either 1 or 0. Okay, so that is the point which we need to keep in mind. And the radix will or base is 2, because it is binary, we have only two values, so base will be 2. So here we need to multiply those coefficients by 2 powers depending on the position of those. Okay, we need to multiply respective coefficients by respective, okay, 2 powers. Yes. Now let us consider, okay, we will consider this octal number system, hexadecimal number system later. So now let us continue with the binary number system. As an example, I will consider a binary string. Yes. So let me consider 101101 dot 0 double. Okay, let us consider this binary number. So let us see how to represent this in the expanded format, okay, using this generalized equation. Yes. So here if you count the digits, number of digits, we have 0, 1, 2, 3, 4, 5. So highest power of 2 will be 5. Therefore, let us start 1 into 2 power 5 plus 0 into 2 power 4 plus 1 into 2 power 3 plus 1 into 2 power 2 plus 0 into 2 power 1 plus 1 into 2 power 0 plus, yes, next we need to, okay, consider the digits what we have after decimal point. So we have 0, 1, 1. So 0 must be multiplied by 2 power minus 1. Then 1 must be multiplied by 2 power minus 2. And again the last digit 1 must be multiplied by 2 power minus 3. Yes. Now let us find out the equivalent value. So when we find the equivalent value, remember, so we are going to get the decimal equivalent of it. Even if you consider the octal or hexadecimal number also, so even in that case, if you write the number in expanded form, using this general representation, then the equivalent value will be the decimal value. Decimal equivalent of the given number. Yes. Now it is in binary. Whatever the answer we are going to get will be in decimal. Let us find out. So we have 1 into 2 power 5. 2 power 5 is 32. 2 power 5 is 32. 32. Next we have 0 into something. Yes, 0 into anything is 0. And next we have 1 into 2 power 3, which is 8. Plus next we have 1 into 2 power 2. 1 into 2 power 2 is 4. Next we have 0. Yes. Next we have 1 into 2 power 0, which is 1. Plus next we have 0 into 2 power minus 1. Plus next we have 1 into 2 power minus 2. 1 into 2 power minus 2 is 1 by 4. 1 by 4 is 0.25 plus 1 into 2 power minus 3. 1 into 2 power minus 3 is 1 by 8. So 1 by 8. So its equivalent is we will get around 0.13. So 0.13. If you want, you can consider one more digit. Now let us find out its equivalent. Yes, we have 32 plus 8. 32 plus 8 is Yes, now let us find out its equivalent. So we have 32, again we have 8, so 32 plus 8 is 40, 40 plus 4, 44, 45, so 45, because we have lesser number here, so I am doing addition from this side. So we need to add, first the fractional values. So if we get carry, we need to consider that also. Yes, here, so we have 0.25 and here we have 0.13. So 0.25, 0.13. So what is the equivalent? So we have 38. So 45.38. So this is the decimal equivalent of the binary sequence, whatever I have considered. So this is about the binary number. Now let us see the representation of numbers in all the 4 number systems. Yes. Now, as I said, if I consider decimal number system, so how many digits we have in decimal number system? 10, right? Then we need to consider binary. Let us write the binary, equivalent for this decimal number system later. So next we need to consider octal. Next we need to consider hexadecimal. Now in this representation, let me consider, since I have hexadecimal number system, in hexadecimal we will be having digits from 0 to F, 16 digits will be there. Therefore, so I will be writing all the 16 digits for that, and again, so equivalent to that whatever the representation we have in octal, that is I am going to write 16 numbers. So in octal number system, even in binary as well as in decimal number system. So let me start from here. Since I have hexadecimal, I will be writing up to 16, even though the number of digits here we have is only 10, that is from 0 to 9. So I will be writing up to 16 because I have hexadecimal in which we have 16 digits. Yes, so 0, 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, continuation. So I will be writing here 13, 14, 15. Since I have started from 0, so I will be ending at 15. So though we have 16 digits there. Okay, for hexadecimal we will be having 16 digits. Yes, so I have written the equivalent of hexadecimal number in decimal number now. Let me write the same 16 numbers in binary. So in order to represent 16 or in order to represent 15, actually not 16, since we are starting from 0, here also we will be having the maximum value, that is the last value as 15. Therefore here 4 bits are sufficient since we can represent the 15 using 4 bits. So I am representing or writing equivalent of these numbers in binary using 4 digits. Okay. Yes, so I have 0, 0, 0, 0 here, next 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 4, next 5, 6, 7, 8, 9, 10, 11. Okay, so I have up to 12 here. So after 9, so I will be writing 1, 0, 1, 0, 10, okay, 11, 12. Fine. So how to write the binary numbers? So you should know how to write the binary numbers for any given decimal number or octal or whatever. Okay, so how it will be done? So for any given decimal number, you need to understand, when you are using 4 bits, just understand the positional weights of this. So we have 8421, we call 8421 code sometimes. Using these values, so you need to represent these digits. Say for example, if you are writing 9, so 9 is nothing but 8 plus 1, by adding which of the digits, which of the numbers or which of the positional values you get the equivalent decimal number, you need to see, and then accordingly you need to write. Say for example, if you are writing 12, 12 can be represented by as a sum of 8 plus 4, 8 plus 4. So we don't require 2 or 1, right? So you need to write 1 in place of 8, 1 in place of 4 and 0 in place of 2, and 1 again 0 should be written in place of 1. Yes, so now if you observe 12, as I said, so so how writing 9, then you need to add 8 and 1. So if you add 8 and 1, we know that, so we can get 9. Therefore you need to write 1 in place of 8. Then you need to write 0 in place of 4. Why? Because I don't require 4. 8 and 1 are sufficient to get 9. Therefore, so you need to write 1 in place of 8, 0 in place of 4, next 0 again in place of 2, and at last 1, because 8 plus 1 will contribute or will result in 9. So this is how we write the binary equivalent for a given decimal number. Yes. So I have written up to 12. Let me continue here. So binary representation 13, 13 is 8 plus 3, 8, plus 3, 2 plus 1. So 3, next 14, 14 is 12 plus 2, 12 is 1, 1, 8 plus 4 plus 2 plus 0. 15 is 8 plus 4 plus 2 plus 1. So this is how we need to write the binary equivalent for any given decimal number. Now let me write the octal number. So octal, how many digits will be there in octal? So we will be having 0 to 7. In binary only 0 and 1. In decimal, so we will be having 0 to 9. Whereas in hexadecimal 0 to F. Yes, octal. So now we have the maximum value what we have is 7. So we need to be careful while writing the number. So in octal representation, how do we write? We write 0 for this, 1, 2, 3, 4, 5, 6, 7. Up to 7 you need not have to worry. You need to just write as we write in case of the decimal number system. But 8. So what is the representation, or how do we write a number after 9? How do we write? We write the number as 1, 0, that is 10, right? So similarly here also after 7 we need to write 1, 0, that is 8. In octal since we have maximum number as 7, so after this next number will be starting with 10, similar to the decimal. 9 after 9, how do we write? So similar to that, so we need to write here also. Therefore, so next number is 10, which is nothing but 8, okay, in decimal number system. You can check that. So how do we check? So if you write the expanded form of that number, you will be getting equivalent of that in the decimal. Say for example, we have 10, so 1 into 8 power 1 plus 0 into 8 power 0. Yes, 1 into 8 is 8 plus 0 into anything is 0, so 8. Therefore, 10 in octal will give you 8 in binary, 8 in decimal number. Okay, let us continue. Therefore, after 10, 8, this is 9, this is 10, okay, 11, we need to write up to 12, right? Yes, let me, okay, 8, 9, 10, 11, 12, okay, next 13, 14, 15, 13, 14, 15. So we can answer. Yes, now let us write hexadecimal numbers. So we have 16 digits, so we need not have to worry here. But again, so here up to 9 we have so we have digits same as, okay, the decimal number, but after that what we need to do here is, so we have symbols for representing the number. So we will not be writing, okay, 10, we will be writing A, capital A instead of 10. So A, B, C, up to 12 we need to write, yes, 12 is, this is 9, 10, 11, 12, okay, yes, A, B, C. And how do we represent 13? D, 14 E, 15 F. So these are the different, okay, the representations, different number systems what we use in the logic circuit or digital, okay. So in the digital design, these are the different number systems we use. So I hope you have understood. So how to write the numbers in binary, how to write the numbers in octal, and how to write the numbers in hexadecimal. Okay. So this is about the binary numbers. In today's session, let us learn how to convert the given number from one number system to the other number system. Today I am considering, okay, so conversion of binary to decimal, octal to decimal, and hexadecimal to decimal. And after, okay, so this conversion I will be explaining how to convert the given binary number into octal and hexadecimal and vice versa. Okay, those are the conversions I am going to discuss today. So now let me consider as an example, okay, the first problem what I have considered is, so I have considered convert the given binary sequence to, okay, decimal number. So I have written here, you can observe here. So this is the way we represent the binary, okay, that is the given sequence should be, okay, written like this. So representing the radix here. So similarly, so in order to represent any number in decimal, we write 10, okay. So this is the way we represent. Now let us consider the binary number. So in order to convert any given number into the decimal number, just we need to express that number in expanded form. In the previous class we have seen how to express any given number, any compact number in expanded form. So if you just express in expanded form, that is sufficient, okay. If you find the equivalent, then you will be getting what is the equivalent for this, okay, binary number in decimal. And similarly it is, okay, true for the octal and hexadecimal also. If you consider any octal number, then you need to put it in expanded form, you need to express it in expanded form. So expanded, okay, after expansion, so if you just find the equivalent value, that is the decimal equivalent of that given number. Now let us see for the binary. Yes, so first we need to count how many digits are there. So we have 5 digits. So 2 power will start from 0. Therefore, so 0 to 4 if you want to represent or if you want to express. So 5, okay, in 5 digits in expanded form, 2 powers will start from 2 power n minus 1. If n is the number of digits, so n minus 1 is the highest power we need to consider. Therefore, so for this 1, okay, first bit 1, so I am considering 2 power 4 because I have 5 digits. 1 into 2 power 4 plus 1 into 2 power 3 plus 1 into 2 power 2 plus 0 into 2 power 1 plus 1 into 2 power 0. Okay, yes. So yes, after decimal point, so remember we need to consider, okay, the powers in negative, that is we need to consider 2 power minus 1, minus 2, minus 3, etc. So here I have a decimal point, so you need not have to put decimal point here. So I will just continue by, okay, putting the plus sign. So plus, yes, 1 into 2 power minus 1 plus 0 into 2 power minus 2 plus 1 into 2 power minus 3. Okay, yes. Now let us find out the equivalent of this. So 1 into 2 power 4, 2 power 4 is 16. So 16 plus 2 power 3 is 8 plus 2 power 2 is 4 plus 0 plus 1 plus 2 power minus 1. 2 power minus 1 is 1 by 2, 1 by 2 is 0.5 plus 0.25 plus 0.125. So 1 by 8, 1 by 8 is, okay, 0.125. Yes, the answer is 16 plus 8, 24, 24 plus 4, 28 plus 1, 29, and the fractional part if we add we get it as 0.875. Therefore, the decimal equivalent for the given binary string is equal to 29.875. Okay, so this is how we convert the binary sequence into the decimal number. Now let us see the next conversion. Next conversion is octal to decimal. So let me consider one simple number in octal number system, and then let me convert that into decimal. So in order to convert into decimal, so from any number system we need to just expand. So let me consider simple example. Let us take 235 in octal and let us try to find out what is its equivalent in decimal number system. Okay, yes, so let us write this in expanded form. So we have 2, so into 8 power, let me write the power later. Next 3 into 8 plus 5 into 8. So it's the power starts from 0, 1, 2. Okay, yes, so here yes, let us find out 2 into 8 square is 64 plus 3 into 8 plus 5 into 1. 64 into 2 is 128 plus 24 plus 5. Okay, so the answer is 157. Okay, so this is in decimal number system. If you consider the fractional part, so let us retain the number as it is. Let me consider the fractional part as 46. So in this case, so this is the given number in octal number system. So we need to expand in a similar way. So 2 into 8 power 2 plus 3 into 8 power 1 plus 5 into 8 power 0. So after that, after the decimal point, so whatever we have, so just we need to, okay, express the powers in negative. So 4 into 8 power minus 1 plus 6 into 8 power minus 2. So here the whole number part, whatever we have, so that will remain as it is. Let us find out the fractional part and let me write, okay, the sum. So 4 into 8 power minus 1, therefore 4 divided by 8. So it is 1 by 2, which is nothing but 0.5 plus 6 divided by 8 power 2. 8 power 2 is 16. 8 square is 64, sorry. So 8 square is 64. So the answer is 0.0. Yes. So plus 0.5. Therefore the fractional part. So the answer, okay. So this will be 157. Therefore, so it will be like, so 157.59375. So this is the equivalent of this number in decimal number system. Okay. So this is how we convert from octal number system to the decimal number system. Now let us see the next conversion, that is hexadecimal to decimal conversion, and for that let me consider one more example and let me explain the conversion procedure. Yes, I have taken A7C, okay, in hexadecimal, and let me find out what is its decimal equivalent. A is nothing but 10. So while writing, we need to write it in terms of, okay, the numbers, the equivalent numbers from the decimal number system. A is 10. So 10 into 16 power 2 plus 7 into 16 power 1 plus C is nothing but 12. So 12 into 16 power 0. Now 10 into 16 square is 2560 plus 16 sevens are 112 plus 12. So the sum is 2560 plus 112 plus 12. Yes, the answer is 2684. Okay, so this is a decimal number system. Now let me consider the fractional part of, okay, and also now let me consider the fractional part in hexadecimal and let me show you the conversion. So if you have, let me consider some other, okay, B, 6, D, F, okay, point. So let us, okay, consider this example in hexadecimal. Now its equivalent can be written as B is nothing but 11. 11 into 16. So how many digits we have? So 4 digits. So 4 minus 1. Okay, 16 power 3 plus 6 into 16 square plus D into, sorry. So D is nothing but 13. So 13 into 16 power 1 plus 15 into 16 power 0 plus next we have 5 into 16 power minus 1 plus 3 into 16 power minus 2. So now let us find out, okay, 11 into 16 power 3 is some 45,056 plus 6 into 16 square 1536 plus 13 into 16 208 plus 15 plus the fractional part 15 divided by 16, sorry, then the fractional part 5 divided by 16 is 0.3125 plus next is 3 by 16 square, sorry, yes, 3 divided by 16 square yes. Now let us see the sum of all this. 0.125 plus 15 plus 208 plus 1536 plus 45,056. Yes, answer is 46,815.32422. Yes, this is the equivalent in decimal number system. Yes, this is how we convert the any given number in these three number system to the decimal number system. Next, let us learn how to convert the given binary string into octal and hexadecimal and vice versa. Okay, and also we have to learn how to convert the decimal number into binary. Next, let us learn how to convert given decimal number to binary number. Okay, so that is also very important. Let us learn how to represent or how to convert the given decimal number into binary number. Okay, yes. So decimal to binary conversion, let me take one or two simple examples. Okay, as an example, let me consider. Okay, so what is the equivalent of 43? Okay, in decimal. Okay, we need to find out, given number is in decimal number system, that is the number is 43. We need to find out what is the equivalent of that number, okay, in binary number system. Yes, so now 43. So how to convert? So we need to divide successively the given number by 2 and we need to maintain a record of the remainder. Okay, that is very important. We need to maintain a record of remainder. We need to note down what is the remainder in each and every step. Then, so we need to read from bottom to top, so which gives us the equivalent number. Okay, so that is the equivalent to the given decimal number. So we have 43. So yes, let us consider the successive division of 43. So when we divide 43, so 2 2s are 2 1s are, remainder is 1. Next again, so remainder is 1. Yes, 2 5s are, remainder is 0. 2 2s are 4, remainder is 1. 2 1s are 2, remainder is 0. See, so now we need to so record this remainders and now we need to read from bottom, and here I am going to write yes, 101011. Let us check whether it is correct or not. Okay, you can cross check here itself because you know the positional values of these binary numbers. So if you know that, you can cross check. So here it is 1, this is 2, okay, and next we have 4. In place of 4 we have 0, so we need not have to consider. Here we have 8, 16 place is also 0, so leave that. Next 32. So if you add up all this, you should get back the decimal number. See here, 32 plus 8 is 40, 40 plus 3 is 43. Therefore, the conversion what we have done is correct. So that verification also you can do. Yes. So this is one example of converting decimal number to binary number. Now, so if you have fraction, so then you need to know how to convert. So that is also very important. Yes. Just now we have seen how to convert a given decimal number to binary number. Now let us understand the procedure for converting the fractional decimal number to binary number. So 348 is the digits whatever we have before the decimal point. Let me consider 348. So 348 first. So we will see how to convert this. So using the procedure what we just learned now, and then we will consider the fractional part and we will see how to convert the fractional part into the binary equivalent. Yes, so 348 we have. So we have to successively divide by 2. So 2 1s are, 2 7s are, then we have 2 4s are. Okay. So what is the remainder we have here? 0. Next, yes, so 2 8s are 16, 2 7s are 14, remainder again 0. So next we have 2 4s are, 2 3s are, remainder is 1. Next, so 2 2s are 2 ones are, remainder is again 1. Next 2 tens are 20, okay, remainder is 1. Next we have 2 fives are 10, so remainder is 0. Next 2 twos are 4, remainder is 1. Next we have 2 ones are, okay, remainder is 0. Yes, how to read? So we need to read from the, okay, bottom to top. Therefore, so let me write the equivalent of this. So what is the equivalent? Yes, let me start from, okay, here 1 0 1 0, yes, 1 0 1 0. Then we have 1 1 1 0 0, 1 1 1 0. Okay, yes. Now we need to learn how to convert this 0.23 into binary. Let me consider the fractional part, 0.23. Yes. So here what we are supposed to do? The procedure for converting the fractional part is we need to multiply by 2 and we need to record the digit which is, okay, before the decimal point. So for example 0.23 is the fractional part. If you multiply, we will get 0.46. Okay. Here I have 0, okay, as the digit before the decimal point. I need to note down while passing to the next step. So what we are supposed to do? We are supposed to pass only the digits after. Okay, you need to make, even if it is 1, you need to make it as 0 and send, okay, to the next step. 0.46 into 2. Yes. So what is the equivalent? 0.92. So here I have 0. Yes, note down. 0.92 into 2. Yes, what is 0.92 into 2? It is 1.84. So what is the digit after, that is before this decimal point? 1. Note down. Pass only 84 to the next step. Okay. Next 0.84 into 2 is 1.68. 1.68. You need to record this digit and pass only 0.68 to the next step. Okay. So again, so 0.68 into 2 is 1.36. So here, okay, I need to consider 1. So this will continue. We need to stop after 4 or 5 digits as required. Yes, now how to read or how to represent the fractional part in binary is very important. We have to see here, we have read from bottom to top. In this case, we need to read from top to bottom. Therefore, all of you observe. So how to write? 0, 0, 1, 1, 1. So this is the binary equivalent of given decimal number. This is the way we convert decimal to binary. So remember, you need to, okay, successively divide the digits whatever we have before the decimal point. If it is a fractional number, then you need to divide successively by 2 and, okay, record the remainders and, okay, we have to read from top to bottom. And in case of fractional part, so you need to multiply by 2 and you need to note down, so what is the digit we are going to get, okay, before this decimal point, and we need to read from top to bottom. So this is the procedure for converting from given decimal number to binary. Okay. We have 0, yes, note down, and next here 0.92 into 2, yes, 0.92 into 2, we will get, see, 1.48. So 1.48, now what we need to record? We need to record this digit. So what we need to carry for the next step? Only, okay, the digits after the decimal point, that is 0.84 need to be carried further and 1 should be dropped here. Yes, now 0.84 into 2, so 4 2s are 8, okay, 8 2s are 16, so we are going to get 1.68. So you need to record the digit as 1, okay, and for the next step you need to send only 0.62. Again here we will be getting 16, 1 carry, so 12, okay, 1.36, yes, record 1 and send 0.32. So this can be continued further. Now we need to, okay, understand how to write the fractional part of the number, because here if you observe we have read the numbers from bottom to top there, so it will be reverse of it, that is we are going to read from top to bottom. So you need to express the fractional part, okay, see here, so from starting from 0 you need to write, all of you observe here how I am going to write 0, 0, 1, 1, 1, and you need to put etc. here, because so conversion is not stopped, because so we have not obtained 0 yet. So sometimes we will arrive at 0, okay, soon, but in this case, so since I have considered some 0.23, so it is okay, and you can stop up to 4 to 5 digits, okay. Yes, so that is how we convert a given decimal number to binary number. So what are the things we have discussed till now? So firstly, we discussed how to convert the given number in binary, octal and hexadecimal to decimal number, and now we have learned how to convert a decimal number to binary number, okay. So that is also we have learned now. Now next conversion, yes, now let us see conversion from binary to octal and vice versa. I have taken 3 examples already, so you can see, so I have written 2 binary sequences and I have written 1 octal number, okay, to show the reverse process of converting from octal to binary, okay. Yes, now what we are supposed to do when we want to convert binary to octal is, we need to make group of, okay, in binary sequence, okay, in binary sequence we need to make a group of 3 bits, okay, group of 3 bits, and we need to express those, okay, each group using octal number system, that is using 0 to 7, okay, the representation what we have, digits what we have in octal number system, we need to represent those, okay, 3 digits using octal number system representation. Yes, now let us see, okay, the grouping, and let us understand how to convert. It is very simple. So hexadecimal conversion as well as octal to binary, binary to octal. So these 4 conversions what we have, it is very simple compared to the previous methods what we have discussed. So here just we need to group and we need to write the equivalent. So that is all, okay. Yes. Now let us start grouping. Now if you consider the, okay, the point, binary point what we have here, okay, we need to group 3 digits starting from here, okay, and after decimal point you should start from here. So that is the procedure, okay. Let us start a grouping from right side, right to left we will move, okay, for the digits what we have before the decimal point and for the digits what we have after the decimal point, okay. Let us move from left to right, so that you need to keep in mind. Yes, so I have made a group of 3 bits here, okay. Next group is this one, and next if you observe, so what we have, so we are left with only 1 bit, but what we are supposed to do, so if you want you can add, okay, 2 more digits which are 0, okay, since it doesn't carry any value, you can add digits like this, or you can simply express 1, okay, it has 1. So whichever is convenient to you, you can follow that. Yes, now to the right side, so that is after this point, so what we are supposed to do, we are supposed to move from left to right. So 1 1 0, then again here I have 1, but I have said you to make a group of, okay, 3 bits, therefore you can add 2 more bits which are 0. Yes, now let me write the equivalent value for this. So here we have 1 0 0, okay. Yes, let us start from here, since we are writing equivalent value, so you can start from here. Yes, 0 0 1, it is equal to 1, 1 0 1 is 5, and 1 1 0 is 6, 1 1 0 again 6, 1 0 0 is 1. Therefore, so what is the octal equivalent of this binary sequence? 156.61. This is the answer, okay. Yes, now let us consider one more sequence, okay. Now to make you understand, I have considered one more sequence. Yes, so for this sequence, so what is the procedure? We need to make a group of 3 bits. So here I have 3, next 3, next 3, next 3. So here I have sufficient bits, so I can, okay, I need not have to add any zeros further. Yes, now if you consider this, here I have 3, so here I have 2, so you can add 1 more 0 in order to, okay, make it a group of 3 bits. Yes, now let us write the equivalent. This is 6, 7, 3, 2, okay, yes, here dot 0, 1 0 0 is 4. So its equivalent is 7 6, okay, 6 7 3 2 dot 0 4. Okay, yes. So this is how we convert from binary to, okay, octal. Now let us see, so conversion from octal to binary. So it is the reverse process of this. So what we did here, we, okay, first group the given binary sequence, we divided the given binary sequence as 3 bits each and we wrote equivalent number. Now we will do the reverse of this, that is for each digit in the octal number system we are going to write 3-bit equivalent in binary. Okay, for each digit we are going to write 3-bit equivalent. So we will be getting the binary sequence for that particular octal number which is given. Okay, yes, now let us see. Okay, let us understand the procedure. Yes, here we have 7, next we have 4, next we have 3, next we have 2, next 1, next 0. Yes, let me write. Okay, you can start from the beginning. Yes, we have 7, 1 1 1, next we have 4, 1 0 0, 3 0 1 1, 2 0 1 0, 1 0 0 1, 0 0 0 0. So I think, so it is easily followed, it can be easily followed. Yes, so we need to write what is the 3-bit equivalent for 7. So we need to consider only 3-bit because so the octal number system consists of 0 to 7. So maximum number we have is 7. So 7 can be represented using only 3 bits. Therefore, so we have to represent all the digits using only 3 bits. Okay. If you consider hexadecimal number system, there we follow the same procedure, but the difference is we make a group of 4 digits, okay, 4 bits in the given binary sequence, and then we write the equivalent of, okay, those 4 digits in hexadecimal number system. Okay. Now let us consider the next conversion, that is from binary to decimal conversion and, okay, the vice versa. So for that I have taken 3 examples here. So 2 for converting from binary to hexadecimal and 1 example is to convert hexadecimal to binary. So let us understand the procedure for converting the binary number to hexadecimal. So here what we are supposed to do, as I said earlier, in this case we are supposed to make a group of 4, okay, digits. So now let me start, okay, from here. So we need to move to the left from this. So 1 0 1 0, yes, 4 bits. Next, okay, again 1 1 0 1, next 4. So next what I have, so here I have written 0 even though it does not carry any value, but so here I have 4, or otherwise if you have only this, so 1 1 0, you are supposed to add one more 0 in order to get 4, okay, digits, binary digits. And let us, okay, complete the grouping onto the, okay, right side of the point also, that is binary point. Yes, here so we have 0 1 0, we need to add one more 0. Yes, now let us write the hexadecimal equivalent to these 4 bits. Okay. Yes. What do we have here? 0 1 1 0. 0 1 1 0 is 6. So I can write 6. 1 1 0 1. 1 1 0 1 is 12 plus 1, 13. So what is the equivalent of 13 in hexadecimal? Okay, you need to remember the table what I have given in the previous class. So for, okay, 13, so what do we have for 10A, next 11B, okay, 12C, 13D. So this is 13, so we need to write D in hexadecimal. Next we have 1 0 1 0, 1 0 1 0 is 10, 10 is A, okay, dot, next 0 0 1 0, 0 0 1 0 is 2, okay, next 0 1 0 0, 4, therefore 6 D A dot 2 4, okay, is the equivalent number for the given binary sequence in hexadecimal number system. Next what do we have? So, okay, next we have another sequence given. So, in binary, yes, let us see, okay, and let us understand. So, how to convert this? Yes, so again group of 4 we need to make. Yes, we are left with only 2. You can add 2 more zeros, okay, or simply you can just write this as 2. Yes, now on this, yes, see, so here the equivalent of this in hexadecimal is 2. Yes, 1101, again I have 13, D, 0111 is 7, 7, here I have 5, yes, again I have taken 1101, so simply I have randomly taken, so I have obtained 2 times D in this, yes, so this is D, therefore equivalent is 2D77.5D. Okay, so this is how we convert binary sequence into hexadecimal. Now let us see the hexadecimal to binary conversion. So it is same as octal to binary, wherein we wrote what is the equivalent for the given digit, okay, using 3 bits. Now we are supposed to write using 4 bits, okay. Yes, here I have 5, next I have F, okay, C, A, B, at last 6. Yes, 5, how it is represented using 4 bits, because 5 can be represented using only 3 digits, but still what we are doing, we are representing 5 using 4 digits, okay, that is the procedure we need to follow. Yes, 01, 01 is 5, next is F, F is 15, 15 is 11, 11, next C, C is 12, yes, so A is 10, B is 11, so C is 12, so 12 is 1100, next A is 10, 10 is 1010, B is 1011, 6 110, but we need to write 0110. Yes, now let us write the binary sequence. So you can, okay, discard this, you can exclude this and write 101, 4 ones, 2 ones, 2 zeros, 1010, then dot 1011, 0110. So this is the binary sequence, okay, this is the binary sequence which is equivalent to given hexadecimal number. So this is the procedure for converting binary to hexadecimal and hexadecimal to binary. So today, in today's session, what are the things we learned? We learned how to convert any given number into decimal number, in the sense if they give the number in binary, how to convert it into decimal number. Next we learned octal to decimal. Next we learned hexadecimal to decimal. So after that, then we, okay, learned how to convert a decimal number into binary. So in which we saw, so for a number which is present before the decimal point, we need to successively divide by 2 and record the remainders, and we need to read from bottom to top in order to express the binary equivalent of it. And if you consider the fractional part, what we are supposed to do? We are supposed to consider fractional part, and we need to multiply by 2, and each and every step we need to write down. So the decimal, that is, we need to write down the digit which is before the decimal point, either 1 or 0 will be getting, we need to write down that, and then while passing to the next step or the next iteration, what we are supposed to do? We are supposed to consider only the fractional part. So even though we have 1.32, we are not supposed to send 1.32 to the next step. Instead 0.32 will be sent and 1 will be, okay, discarded. So 0.32 into 2, again we need to consider. So we will have to find out what is the product of it. Next we need to find out what is the digit what we have before, okay, the decimal point. So this is the procedure we follow, and once we are done with it, because fraction will yes, so the fraction will keep on continuing, therefore we need to stop at a point. Sometimes we may arrive at 0, or sometimes we may have to stop, okay, after getting 4 or 5 digits, okay. Yes, so then we need to express the fractional part along with the, okay, the part what we have before the decimal point. So that is the procedure. Next, so what we learned, binary to octal, binary to hexadecimal and vice versa. So all the conversions have been discussed. Okay. So now in next class let us understand the complement. Okay. So we will discuss about the complements and how to use those complements in subtraction. So these are the things we will be discussing in the next class. Thank you.